Morning everybody. A lot quicker lesson today, hopefully. So what we're going to have a look at today is angle identities and de Moivre's theorem. Essentially this is an application of de Moivre's theorem to help out with some issues. So we're going to just do two examples today. And before I do the second, I do need to just show you something. The first example is going to be express cos 3 theta in terms of cos theta. So the best way to start thinking about this is by thinking, well, is there anything you know that links these two things together? And yes, there is. It's at the top here. So instead of attacking the question head on, what we're going to do is think, okay, well, if we've got cos 3 theta, then the thing that might help us here is cos 3 theta plus I sine 3 theta is equal to, well, using de Moivre's theorem, de Moivre says that this is the same as cos theta plus I sine theta, all cubed. Okay, so at the moment this isn't very useful, but actually, if you think about it for a minute, we're almost already finished. And the reason for that is cos 3 theta is the real part of this left-hand side, and sine 3 theta is the imaginary part. So if I want to find out what cos 3 theta is in terms of just cos thetas, what I can do is expand this right-hand side out and find out which bit is the real part. So let's expand this out. A shorthand you can use here is cos theta equal to C and sine theta equal to S. And that's only for a theta, not for multiple thetas, just for one theta. So that's going to be cos cubed plus, we're cubed, aren't we? So let me just remember 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. Yeah, that's right. Good. Cos squared I sine plus 3 cos I sine squared plus I sine cubed. Okay, so that's just expanding that out using the binomial expansion. That gives me cos cubed. This bit, there's no power on the I, so this is going to stay as a real, sorry, as an imaginary, so it's 3 cos squared sine I, put the I at the end so it's easy to spot it. This one, the I is going to be squared, so actually this should be minus 3 cos sine squared. And this one, the I is going to be, well, two of the I's will end up making it a minus, and the third one will make it imaginary again, so it's going to be minus S cubed I. So collecting those things together, we get cos cubed minus 3 cos sine squared plus 3 cos squared sine, take away sine cubed, and that's all I. Should probably make my C's and I's a bit clearer, shouldn't I? So therefore, cos 3 theta, I know what I'm up to now, cos cubed minus 3 cos sine squared. However, the question said explicitly to put 3 theta in terms of cosines. Now at this point I would probably start swapping back to cosines and sines in full as opposed to C's and S. The C's and S's are useful particularly for the binomial expansion bit. So what have we got? We've got cos cubed theta minus 3 cos theta, and then we've got sine squared theta, and sine squared theta is the same as 1 minus cos squared theta. So altogether we get 3 cos times that one gives me 3 cos cubed. That gives me 4 cos cubed theta altogether minus 3 cos theta. So I've managed to express cos 3 theta in terms of just cosines, and when I said therefore here, all I did was I equated the real parts. And hopefully you can see from here that if you were asked to write sine 3 theta in terms of just sine thetas, you could do that also. Here's the imaginary part here. Cos squared is 1 minus sine squared, so you could do a very similar process to find out what sine 3 theta is. Okay, so I just realised I've inadvertently done question 1 from the book. It's a bit of a shame. So what I'd like you guys to do before we do the next bit, can you please show, or can you, yeah, so can you express cos 5 theta in terms of cos theta? And just so you know, so you can check that you've got it right, you should get 16 cos to the 5 theta minus 20 cos cube theta plus 5 cos theta. So have a go at that, just make sure you've got that right, and then once you've done it, come back to the video, please. Okay, so I hope that went well. I think I've inadvertently now done question 8 as well. I really need to start picking decimal numbers. So what we're going to have a look at next is 2 forms of cos n theta and sin n theta, which are going to help us with our next problem. So what I've written down on the page isn't news to anybody. It's just De Moivre's theorem. And what I want us to, sorry, that's not, if z is this. So if z is cos theta plus I sine theta, that's better, then this is true. And we've already seen that if I put a minus there, then this becomes this. Try that again. And that's just by using the fact, using the ideas of odd and even functions. So what I'd like us to have a look at next is adding these 2 expressions together. And if we add these 2 expressions together, we get z to the n plus z to the minus n. And if we add the right hand sides together, we're going to get, 2 cos n theta and hopefully you can see from there, then that implies that cos n theta is equal to zn plus z minus n over 2. What I'd like you to do next is, instead of adding them, can you subtract them instead and find out what sine n theta is equal to. Let's pause the video and have a go at that. So if you subtract them instead, you'll end up with this z to the n minus z to the minus n all over 2i. Okay, so these 2 things you should really know, and you should particularly pay attention to the fact that cos of theta equals z plus z to the minus 1 over 2, for example. We're going to use this for a particular example. So the next example is this one. It's expressed cos to the power 5 theta in terms of cos n theta, and we can have any combinations of whole number n's here, so it could be 1 theta, 3 theta and 5 thetas. We can have combinations of them, it's not an issue. And so the way we're going to do this is as follows. So if we let z equal cos theta plus I sine theta, I know there wasn't a z in the original question, but we're going to try and generate a cos to the power of 5 theta somehow. So if we let z be this, then we know from what we've just done that 2 cos theta is equal to z plus z minus 1. Now this is a slightly rearranged form. In this form we've got a 1 in here, so these are to the power of 1 and minus 1 respectively. But I've just rearranged it slightly to get the 2 up here. And what I'm going to do is I'm going to just raise both sides to the power of 5. So I've got 2 cos theta to the power of 5 is equal to z plus z minus 1 to the power of 5. And hopefully from there you can see that I get 32 cos to the power of 5 theta is equal to, and then I've got this which I can expand out using the binomial expansion. And because of this is z to the minus 1, lots of things are going to cancel out. So before I start, let me just remind you what the fifth row is a Pascal's triangle. Not that. 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Okay, so 1, 4, second, third, fourth, fifth. I need to go one more, don't I? So that's 1, 5, 10, 10, 5, 1. Okay, so these are going to be my coefficients for my binomial expansion. So I'm going to get z to the 5 plus 5 lots of z to the 4, z to the minus 1, plus 10 lots of z to the 3, z to the minus 2, plus 10 lots of z to the 2, z to the minus 3, plus 5 lots of z, z minus 4, plus z to the minus 5. And what we can do with that is just rearrange things slightly. Well, actually, let's just do some cancelling first. Z to the 5 plus 5z cubed plus 10z plus 10z minus 1 plus 5z minus 3 plus z minus 5. Okay, so if you haven't already noticed, this creates quite an interesting pattern. I've got a z to the 5 here, and I've got a z to the minus 5 here, I've got a 5z cubed here, and a 5 to the z minus cubed there, etc, etc. And so what I can do is I can put these things into their natural pairings. So I've got z to the 5 plus z to the minus 5. I'm going to bracket that just to accentuate that point. I've got 5 to the z cubed plus 5 to the z minus 3. And I've got, I'm just going to write the 10 on the outside because I should have done with the previous one. Z to the minus 1. Okay, so this is really useful now because I know what these individual things are. If I go back to this line up here, the general form of this is 2 cos n theta equals z to the n plus z to the minus n. And so this one here, this bracket here, if I put 5 in here, I'm going to get 2 lots of cos 5 theta. This one's going to be, well, imagine the 5's on the outside, it's going to be 5 lots of, put 3's in here, so that's 2 cos 3 theta. 5 times 2 is 10, so that's going to be 10 cos 3 theta. And last but not least, I've got this one, I stick the 1's in, so that's going to be 10 on the outside times the 2, which should give me 20 cos theta. Okay, so what I've done so far, I've found out that 32 cos to the power 5 theta is this. And what I wanted to know what is cos to the 5 theta. So all I need to do now is divide through by 32. You'll need a connector here. Therefore, cos to the 5 theta is equal to. Now you can just take some 2's out. So we end up with cos 5 theta plus 5 cos 3 theta plus 10 cos theta all over 16. Okay, so what I'd like you to do is go to exercise 10.3. You've done question 1 already, but there is a little bit extra on question 1 which you can finish off. So I'd like you to try and do question 1 to 8 and exercise 10.3. And if you've got any questions, please email me. And I'll speak to you guys again soon. Thanks very much. Take care. Bye-bye.